All right, we're live. We got Steve in the house and Laurel. Excellent. I was running around here. I was running around and because I had to get my coffee pot set up. I had my coffee pot upstairs, had to bring it down, had 4 minutes to go, got it done. Today, welcome to another IAEI News Live. My name is Thomas Dimitrovich. Zen. It's 12 o'clock. And you know what that means? It's 12 o'clock on Tuesday. It is Tech Tuesday. So we're going to talk about Article 240. We're going to go into Article 240. Remember the last, what was it? Last couple sessions that we've done. Let me get this. I heard something in the background. I knew, oh, I need to move this over here. Last couple sections. Hey, Michael Hufkin. Greetings and salutations. There we go. Boom. There we go. All right. And we got Brandon Reed in the house. Thanks, Brandon, for joining in. Now, if you recall, over the last couple sessions that we have discussed, we hit ampacity. I think we did. I got to go to our YouTube channel. I know we've hit ampacity. I believe we did. Hold on, switch account. I got to go to IAEI. And then I go to here and I go to YouTube Studio. So I know we hit ampacity. We talked about, wow, we've got 14,500 people, followers on IAEI's YouTube site. That is absolutely awesome. All right, so last few weeks, here we go. We did ampacity. We talked about how to read a time current characteristic curve because that is relationship to protecting conductors. We talked about proper application of circuit breakers in our last discussion. And now we're going to get into overcurrent protection, Article 240, and we're going to focus in on 240.4. And the reason I want to focus there, I've had questions in the past, and I went back and I found an old, I say old, I don't know what year this was, 2012. Now, if it wasn't 2025, I'd say that was just like yesterday, but this is 2012. I would get questions, I used to get questions about the protection of what's on this side of the receptacle. So I had put together a slide deck that spoke to that, and I will show you what I'm talking about. So this was a slide deck. This goes back to 2012, and I was talking about the attached conductors because, hey, happy Tech Tuesday. We got Willie Snyder in the house. So I would get questions about the conductors that of, like, say, a lamp cord or whatnot, and the proper overcurrent protection based upon Article 240, because actually 210.20, let's take a look. I am using the 2023 NFPA Link 2023 National Electrical Code. And if I go to 210.20, it's probably still the same, overcurrent protection. And what it tells us is branch circuit conductors and equipment for circuits not exceeding 1,000 volts AC or 1,500 volts DC shall be protected by overcurrent protected devices that have a rating or setting that complies with 210.20A through D. So in 210.20, it says my branch circuit conductors and equipment. Well, when I hear and equipment, is that equipment that's plugged into the receptacle? Right? So this was the question, some of the questions that I would get back in the day. And in this 210 branch circuits, in 210.20D, show you what I'm looking at. In 210.20d, it says, the rating or setting shall not exceed that specified. Equipment. The rating or setting of overcurrent devices shall not exceed that specified in the applicable articles referenced in table 240.3. And then in conductors, it said conductors shall be protected in accordance with 240.4, which is what we're going to talk about. And flexible cords and fixture wires are protected in accordance with 240.5. So I would be amiss if I said we weren't going to also take a look at 240.5. Okay, so I want to look at 240.4 and I want to look at 240.5. And I can tell you that my journey in this area started a long time ago. At least back to when I made this presentation, probably well after I was getting the questions. But I would get these, and here's the image. This was from my office back in Charrington in our facility. I took a picture and I said, all right, so I plugged this one in. It was a heater that I had under my desk. This is a porcelain heater. So I had that plugged into the multi-tap, this outlet, and then I diagrammed the panel board, installed NM wire, and I had the connected cord, and the argument or the discussion that we would have is the cord that's on this, I'll call it an appliance, a heater, on this heater is definitely not the same size as the branch NM wire that's behind the wall. In this case, it probably was not NMB. But hey, Don Gannier, good morning, sir. Good afternoon, I think. Good afternoon. But in any case, so I would get this question and say, well, 210 says we need to provide the protection. And how do we protect these cords? So I took my initial journey back in the day to help address that. So that's where I'm coming from today. I want to explore 240.4. We're going to dabble in 240.5 in our discussion. All right, so hopefully you have your, give me 1 second. Keep my coffee pots numbered for just such an emergency. All right, so I'm gonna have to have a cup of coffee because after this I have another 2.5 hours of working with a consulting firm talking about code. So I'm gonna need a lot of coffee. All right, so got that puppy down. All right, so let's dig in. If I go to 240, remember Article 240 is overcurrent protection, right? Yes, overcurrent protection. I always got a question. Remember, believe half of what you see and less of what you hear. Verify for yourself. And if you have questions, send them to me. You guys know who I am. Send me a note. Send it over to Laura. Send it to IEI. They'll get it to me. Say, hey, I got a question for Tom. Right? All right, so 240.4 is titled Protection of Conductors. You have a receptacle, not an outlet. That's very good. You are a very good. It wasn't a receptacle, really. It was a receptacle, but it was a what do they call that? A multi-tap? Multi-tap receptacle? What is it? Michael Hofkin in the house. What is it? A multi-tap receptacle? Yeah, multi-tap outlet. Multi-tap, it says, oh man, Amazon calls them multi-tap outlets. Multi-tap outlet with multiple receptacles. You gotta love this stuff. Well, you will bring this stuff up, wouldn't you? Yes, you would. All right, so 240, let's go back to 240.4. All right, 240.4 tells us that conductors, and I love this, it says, other than flexible cords, flexible cables, and fixture wires. So we know 240.4 does not apply to flexible cords, flexible cables, and fixture wires. Where is that? I mean, somewhere there has to be language to protect flexible cords, flexible cables, and fixture wires. Where is that? 240.5. And that's why that is why right over here we had in 210.20, it tells us conductors shall be protected in accordance with 240.4, but it says flexible cords and fixture wires shall be protected in accordance with 240.5. And I have on my slide, 240.5 reveals some interesting facts about overcurrent protection of flexible cords and fixture wires. 240.5 Bravo. Okay. I love this. Okay, this, you can't make this stuff up. I love this stuff. I don't know who out there loves the code, because just when you thought you knew it all, wham, somebody comes in with a curveball. Okay, so if I look at the language in 240.5 Bravo, it says where flexible cord or tinsel cord is approved for and used with specific listed appliances or luminaires, it shall be considered to be protected when applied within the appliance and luminaire listing requirements. So what this tells you, and this is a theme. This is a theme in the code that you've got to honor and respect. You've got to apply products as per how they were listed and tested. Michael Hofkin, you can speak to this every day of the week, twice on Sunday. If I test a product in a certain way, under certain conditions, the code is going to help you follow those rules to make sure that you apply that product, or yeah, I'd call it a product because everything's a product. I mean, whether it's a conductor, terminal, cable, breaker, panel board, switchboard, switchgear, those are all products or electronic components. You've got to apply them as they were listed and tested. Those two go hand in hand. And I know UL goes through painstaking review of all of the code requirements to make sure that the standards reflect what the installation requirements include, and vice versa. If there's a change in a standard, or if there's a new product that hits the street, I know UL Solutions does a really great job, a stupendous job. Sometimes they don't get it right, but none of us do. But in most cases, they'll get that ball rolling, and we will come to good language, or language that will get better with time. That's the way the code goes, right? So you'll get language that is in there that reflects the installation requirements. And I know, Michael, we were just talking about you. Truth, the installation instructions are part of the listing. Exactly. And so it's very important that the installation requirements and the UL standards align with each other. So, and I know, again, that UL is heavily involved, and you're right, you have heavy representation on all the code making panels. I know I work closely with guys like Tom Lichtenstein, and Robert Osborne and Donish Zia and Fred Reyes, and there are a myriad of UL Solutions people that sit on these code panels, as well as Intertech and others, and all of these individuals who represent the standards on how products are tested make sure that they're applied per the requirements in the code. Okay, now let's go back to 240. So I think it's clear when it comes to listed appliances or luminaires. In fixture wires, they have requirements in fixture wires. Extension cords. Oh, I get this question a lot, and I love this. I love this. This requirement in 240.5b. 3, flexible cords used in listed extension cord sets shall be considered to be protected when applied within the extension cord listing requirements. So we have to We assume it's protected when we apply it correctly. I don't believe there is an instruction sheet out there that tells you on an extension cord you can put it under a carpet or use it as part of permanent wiring, right? They expect that these extension cords are in free air and they're temporary in nature, okay? So when you look at the requirements, if you apply it correctly, we assume it is protected. Now, I think you can also buy solutions that may have built-in ground fault protection. Okay, I've seen those and all that jazz. Felix Sandoval has a question about, now I know we're talking about 240.4, but he has a question about 240.41. I think it's 41. 240.41. And I should have my Shock Week mug, but I grabbed a different one. Arcing or suddenly moving parts. Arcing or suddenly moving parts shall comply with A and B. Fuses and circuit breakers shall be located or shielded so that persons will not be burned or otherwise injured by their operation. And then B, suddenly moving parts, handles or levels of circuit breakers and similar parts that may move suddenly in such a way that persons in the vicinity are likely to be injured by being struck by them. I would love to see the circuit breaker that handles, moves, and will hurt somebody when it moves, shall be guarded or isolated. You know what? They might be talking about those extensions that are on a handle of a circuit breaker. What happens in a PV modules? Oh, 240.21. 240.21. Overcurrent protection shall be provided in, so in PV modules, so what you're saying, Felix, and it looks like you corrected yourself in 240.21. In PV, I would go for photovoltaic systems, I would go to 690. They have requirements back there for protection of conductors. You follow the rules in 690. They'll tell you where the overcurrent protected devices need to be located. We can do a program on that one, Felix, but I would say I would look in 690 and in Article 705 for interconnected systems. They'll have information in both of those locations to address the location of overcurrent protected devices. All right, so 240.4. Let's go back to 240.4. We diverged. We digressed. All right, so 240.4 is protection of conductors, and it says that conductors other than flexible cords, flexible cable, shall be protected against overcurrent in accordance with their ampacities specified in 310.14. And it says unless otherwise permitted or required in 240.4a through h. So in 310.4, now 310.14 talks about the ampacity of a conductor. Now we talked about the ampacity, right? We talked about ampacity, and we have a definition of ampacity. It's the maximum amount of current in amperes that a conductor can carry continuously under specified conditions of use without exceeding the conductor temperature rating. So the conditions of use and the discussion of ampacity in 310.14 is around the conductor. It's not about the motor. It's not about the transformer. It's not about the panel board, the circuit breaker. It is about the conductor. And what we know is that the ampacity values in table 310.16 are based upon a condition of use, which is defined in the title of table 310.16. And those conductors, under those conditions of use, can handle the amount of current based upon the insulation rating of the conductor and how it's applied. When I say how it's applied, like if you have it in water, right? So some of the ampacity values of, like, say, not THHN, but one of those, a few of those insulation types may be, they may tell you in table 240.2, no, 240. No, it's not 240. It's 310. Is it 310.2? 310? Hold on. 310.2. 310.3 will tell you in some cases you may have an insulation rating. If it's in water or direct buried, it's based on the 75. If it's not, if it's dry and not a wet location, if it's a dry location, then it would be based on 90 degrees C, but it's the same insulation. So you got to just be careful on how you apply that. But the fact is that when we talk about ampacity of a conductor, it is the conductor that we're talking about, and it's the conditions of use. So the table 310.16 will give you a specified condition of use, and 240.4 tells you that you need to protect a conductor in accordance with the ampacity of that conductor. And because they point to 310.14, that tells you that it must take into consideration the conditions of use. So a conductor, now we're talking conductor protection, a conductor can be protected at its ampacity, which if I take a THHN conductor and I put it in an environment of 120 degrees Fahrenheit, if I put it in a raceway with 5 other conductors, now I am impacting the ability of that conductor to carry current, right? Laurel says UL 62 for flexible cords and cables, Article 400. Oh, very good point. You got to go back there. Very good, Laurel. And in 310.41, conductor applications and insulation. Yes, 310.4. Yeah, oh, that's where it's at. I thought it was a 310.3. No, you're right. 310.4, that's it. That's the table 310.41. Thank you, Laurel, for that correction. 310.41 will tell you, in fact, let me give a good example, because this was one of those where I said, wow, I have the same insulation, and depending upon where I install it, if it's in a dry or a wet, THHW. There we go, THHW. This is a good point. So here is THHW. So if I have an insulation that is THHW, and I can say, oh, it's 90 degrees C insulation, but when it's in a dry location, it's 75 degrees C when it's in a wet location. So I got to be careful. I don't have a dash anything bad. I don't have a -2. I don't have anything. I just have THHW. So I've got to be careful when I think about the ampacity of that conductor and the starting point for the derating factor. So to protect a conductor at its ampacity, it is critical for us to understand how to determine the conductor's ampacity, right? And the conductor's ampacity is only based upon what you see in 310.14, which is ampacities for conductors rated 0 to 2,000 volts. So you have A is in general, it tells you engineering supervision, so you can, as long as you have an engineer in the room, you cannot do anything wrong because they are in the room with you, okay? So, and they're supervising you. That means that they're watching you. They're sitting there drinking their coffee out of their brown coffee mug, and they're going, yep, I watched him all day. He didn't make a mistake one time because I was there. So you got tables or engineering supervision, and they point to 310.15 and under engineering supervision as provided in 310.14b, the ampacity with more than one where more than one ampacity applies for a given circuit length, the lowest value has to be used. So, and what that means is, let's say I have a conductor that goes from my conditioned room, my dry location. It leaves here, goes into a raceway outside, and now it's a wet location. And then it comes back up and it goes into my garage, which is a dry location. And for that length of conductor that's in the wet location, I'm limited. Say I had that THHW, and it said if it's in a wet location, it's 75 degrees C column, and I'm limited to the 75 degrees C for the ampacity of that conductor. That's my limitation. If I leave this beautiful room and I have 3 conductors, and then they leave this room, go into another room, and they enter a raceway for about 50 feet with 3 other sets of conductors, my point of my ampacity is going to be adjusted for that length of the conductor that is in a raceway with all of those other conductors, because now I've got to go back to the number of conductors in a raceway. So remember, I can adjust these ampacity values based upon temperature and based upon the number of conductors in a raceway. So now they'll tell you as an exception to the ampacity, when you have a circuit length, there's an exception that says that as long as you don't exceed 10 feet or 10% of the total circuit, then you don't have to worry about that portion, which is in that restricted zone. So Don Ganir, now you may get to use the exception in 310.14a2. Yes, and that's what I was just talking about. So the delay is beautiful, and it tells me we're both thinking the like, Don. So that's right. So you can use that exception if it says where different ampacities apply to portions of a circuit, the higher ampacity shall be permitted to be used if the total portions of the circuit with the lower ampacity doesn't exceed the lesser of 10 feet or 10% of the total circuit. Okay, so that gets, you know what that does, Dawn, and you know this better than I do, that gets you out of having to adjust the ampacity because you have a portion of it that maybe goes through a stud or a joist. You may have a bundle of conductors maybe in the panel board before they even leave. So you don't have to adjust for those instances where you have just a very short piece of the conductor. So in any case, that's the exception in 2. Now, in A3, it says temperature limitation of conductors. No conductor can be used such that its operating temperature exceeds the designated type of the insulator conductor involved. So that's where the importance, Laurel, of in 310.4, that table, to make sure that you understand the insulation and the limitations of that. So good point. Dawn says, very often used in a wireway above a panel. Yes, that's what I knew that. I knew a panel board and that the wireway above a panel board, very, very good example for that. No conductor shall be used in such a manner that its operating temperature. Okay, so you can't exceed the ratings of the conductor, right, and the markings. All right, so then I'm not going to go through the engineering supervision. You can calculate, etc. So that's basically 310.14. It speaks to the number. It speaks to the ampacity value. So how do we get there? Let's go back to 240. 240.4. Oh, that was in the parent text of 240.4. As specified in 310.14. So what gets me to 310.15? Let's go back to 310. So if I look at 310.14, it tells me I've got tables. It tells me I select my ampacity. That's that weakest link, with regard to the conditions of use. I've got temperature limitations of the conductor. I have an engineering supervision, but where Do I get into the ambient correction factors? I guess that's just in the general ampacity of the conductor. 310.15 is where I'm going to, I would have expected in 310.14 for it to tell, oh, it does right there. Well, it's the tables as provided in 310.15. So it says ampacities for conductors shall be permitted to be determined by tables as provided in 310.15, but it doesn't tell me about in 310.14 that I need to adjust it for the conditions of use. I've got temperature limitations. I've got the selection of the ampacity. I would have expected something in 310.14 to tell me that the ampacity of my conductor is based upon the conditions of use as governed by 310.15. And I'm not seeing it. It just says the tables of 310.15. It doesn't, and in 310. Okay, so if I go to the tables, I get it. I get it. If you go to the table in 310.15, the title of the table, in fact, I have a slide on this. The title of the table, there it is. So it tells you the title of the table, ampacities of insulated conductors with not more than 3 current-carrying conductors in a raceway. The notes to the table put you back to 310.15 for the adjustments. And then, so that's the conditions of use. And then I have my insulation, but I also have a note. I also have a note for the ambient at 86 degrees Fahrenheit. So I have the conditions of use in the title. It tells you no more than 3 current-carrying conductors in a raceway. And then I have the temperature adjustment that tells me that these values are based upon 86 degrees Fahrenheit. So if I have an elevated temperature, I need to adjust these values based upon the elevated temperature. All right, 310.15a. Yes, Freddie B in the house. Laurel, yes it does. Look at 240.4, right-hand column, hiding under the table on page 122. 240.4. 240.4. I'm gonna go there, Laurel. I am going there. 240.4. You said hiding under the table on page 122. I don't have my book. I'm not seeing it. I'm not seeing it. But I believe you. I believe you. 310.15, 310.15. All right, so I have my conditions of use, and then I have my temperature, my insulation ratings, I have my insulation types, and then I have my conductor materials, whether it's copper, aluminum, or copper-clad aluminum. I got my sizes. I have my ampacity values that are based upon those conditions of use and 86 degrees. Oh, yes. Okay, I see what you're saying, Laurel. I see what you're saying. You're saying it's the last, it's where it says in the charging statement of 240.4, ampacities specified in 310.14 unless otherwise permitted and required in 240.4a through F. And 310.14 is what we just reviewed. And then 310.14 points you to the tables in 310.15, and the tables tell you you need to adjust the conditions of use, or sorry, 310.16, and then the tables tell you that you need to adjust the use based on 310.15. Perfecto. Muy bueno. What is Eric Marino? What is good practice when choosing ambient temperature? Should I use the highest recorded temperature or the average? Ooh, that is a really good question. What do you guys and gals do out in the field? I had a similar question with water level in marinas. What do you guys do and gals do for the ambient temperatures? I know there was a site, I think it was there was a site for like for example, attics. What typical attic temperatures in summer in Georgia. Let's just pick Georgia. I know there was a website that gave some averages, and I can't remember who that was from. Salsa, Mr. G, you need to follow IAEI News Live. You got to follow IAEI News Live. Eric, that's a really good question. I'm going to take that on advisement. I will try to do some homework. And I know there was a website that I looked at, and I can't remember where it was, that gave typical temperatures. I know there's ambient temperatures in the environment, but there was a reference that I was using that I remember an inspector used for attics, and I can't remember what it was. So anyway, because it's really important to understand what you could see in an attic, because you could have conductors that are in the attic. You could have the supply and the load in an attic, in an area of the house that's not conditioned, and you need to take that into consideration when you're sizing the conductors for the application. Very good point. Eric, I wish I had a better answer for you. We'll see what everybody says. Yes, it does. Yes, I always remind myself of the need to read the whole article and the tables, annexes. Yes, absolutely, Steve. Absolutely. Ashray. Yes, Ashray might have. So Mr. G, you said, no, it wasn't Mr. G. Who asked? Steve. Who asked about the temperature? So Fred, summer roofs upstate gets hot enough to cause second-degree burns on bare skin. Wow. Ashray tables for outside temperatures designed. But Dawn, what do they do for an attic? What is the adder that you put in for the Eric? Thank you, Eric. There's an adder that they put in for attics. I can't remember where I got that from. Controlling ambient temperatures requires temperature control systems to be put in place as a means of mitigation. That's right. So when you don't have that, then you need to take that into consideration. All right. So proper conductor protection begins with proper conductor selection and application, right? So I need to be crystal clear on how I determine the ampacity of a conductor to make sure that I can protect it at its ampacity. Now, 240, now remember, so 240.4 tells me in the parent text, I need to protect it in accordance with the ampacity. And that's, it's a simple sentence, but it is so complicated because it gets you into 310 to make sure that you are selecting the right conductor for the application and you are adjusting its ampacity accordingly. And this entire discussion has nothing to do with what's connected at either end of the conductor. Zip. It has nothing to do with what's connected at either end of the conductor. The ampacity of the conductor is the ampacity of the conductor based upon, just like it says here, 310.14, which points you to 310.15, which points you to the tables and the conditions of use. And nowhere in this picture do we have anything that says I have to protect a motor, or I have to protect a fan, or an HVAC unit, or whatever it is. Has nothing to do with what's connected on either end. I've got to consider that ampacity of that conductor based upon its conditions of use, which are defined by table 310.16. The number of current carrying conductors in a raceway and its ambient temperature that we expect it to be in. There are a lot of questions around ambient. I agree. And I would argue, and I wish I had a better reference for, like if I'm in an attic. I know my attic, I don't get up there in the summer. I pass out in an attic. And you got to be very careful when you're crawling in those attics because it is hot, okay? But if we have wire up there, and if it's more than 10 feet, or 10%, or if the origin and the destination is all in the attic, 100% of the wire and the components are in the attic, and a good example would be what? An attic fan. You may have a disconnect up there for the fan, or an HVAC unit that might be in the attic. All of those types of solutions, I need to make sure that I consider the ambient temperature that's in that attic, which is not going to be 86 degrees Fahrenheit. Steve says, for ambient, you have to determine which extreme creates the greater hazard, which is almost always heat. Cold breaker, even if conductors are inside. So, Steve, that's a good point. Now when you get outside, now, be careful. And the only reason I'm saying be careful, we're talking about conductor protection of the conductor, so we're determining the conductor ampacity. Has nothing to do with what's on either end. I agree with you that the temperature, I will have limitations for the proper application of my overcurrent protective devices, whether they're fuses or breakers. I will also have limitations of application of the loads, which may be HVAC, it could be fans, could be a motor. I have to consider operating that equipment, appliances, in the elevated ambience as well. But what we're talking about right now is protection of a conductor, period. All right? But very good point, Steve. Very good point. Mr. G says, this topic becomes a validation of what I've been trying to convey for years now regarding the lifespan of conductor insulation and accelerated yes. You know what? Send me an email. Send me an email on that because I want to explore that with you a little further. I want to do a little bit more homework on that. I have some theories, but I have no evidence of it. But a good question. And I had a really good, healthy discussion with an individual just today. And we were talking about what is the impact of the elevated temperature on these components. If I apply, say I don't have a 90 degree C, let's say I have a 75 degree C insulated conductor and I put it in 90 degree C, or I use it above its rating. It's not going to immediately fail. What is the long-term implication to the misapplication? We test our products, we test our solutions, all of the different things that we have out there, whether it be a coffee pot, it be your cell phone, right? These solutions are all tested based upon a given set of criteria, which is probably against some standard, product standard somewhere. More than likely, if it's an electrical product, it's going to be on a UL standard. And in fact, if it's an appliance, it's probably a UL standard too. But what happens when you misapply it? We don't test for the misapplication. We just say, hey, look, here's the constraints, here's how we test it, and we expect you to install it this way. What happens if you exceed that temperature by 10 degrees, by 50 degrees, whatever it is? What happens if you exceed the current on that conductor by 2%? Does it reduce the life of that conductor? Does it reduce the life of the circuit breaker? What's the end failure mode? Nobody knows because nothing's tested that way, but I would love to understand a little bit more where you're coming from, Mr. G. Freddie B, attics easy times get to 120 degree range. Yes, I've heard as high as 150 in some locations like Arizona, Texas, even Georgia, and places like that. So, you know what, this is going to make me want to get one of those temperature devices where you throw it in an attic and just let it sit there for a year in a bunch of attics across the country and then come back in a year and say, okay, here is the highest temperature that we saw. Froming in the house. Most wires in attics are below the insulation and not too hot. Below the insulation. I'm not sure what that... I'm not sure. If I do 90 degrees C, 90 degrees C is 194 degrees Fahrenheit. And I would agree, if it's below the insulation, 194 degrees is still hot. So if it was 150 or 140, it's pretty freaking hot. And Steve, you would have to adjust the ampacity because that 90 degrees C insulated conductor, the ampacity is based upon 86 degrees Fahrenheit, right? So you would need 84 to 86, I think is the range. So if it gets hotter than 86, you're going to need to reduce the amount of current passing through that. But I probably tend to agree with you that you're not going to exceed 194 in an attic. If you've got more than 194, then you've got other problems, right? I would agree with you there. Don Gannier, for the brand breaker, 400 amp breaker will have a trip point of 500 amps or more about 5 months of the year based upon. Excellent. My previous post should have specified an outside breaker. Seeing what you were saying, 20-year right ambient temperature versus 20-year normal temp becomes much more brittle. Yep. I will definitely send you a solicited email, and or they would tell you that they would surely be embarking on. Yeah, that would be. I'll enjoy that discussion. Okay, so I can get lost in the comments. I love the comments. All right, so now let's go back. So protecting, now let's go back to 240. 240.4. We've got to protect it in accordance with their ampacity, and we just had a great discussion about adjusting the ampacity. A tells us, in 240.4, A tells us that a conductor overload protection shall not be required where the interruption of the circuit would create a hazard, such as a material handling magnet circuit or fire pump. Oh, okay, so fire pump. So, and it says this is the overload protection. So your short circuit protection has to be there, but you're not going to have an overload protection like on a fire pump. And you would follow the rules in that article for fire pumps. 240.4b, Bravo, overcurrent devices rated 800 amps or less, and C is overcurrent devices rated over 800 amps. Overcurrent devices. So we went from protection of conductors. Okay, so what this is talking about, this is still protection of a conductor. It says the next higher standard overcurrent device rating is permitted to be used above the ampacity of the conductor. So this only applies to the ampacity of the conductor. I have seen people apply this incorrectly. And remember, the ampacity, if I have a 90 degree C insulation, I'm using the 90 degree C column. I'm adjusting the ampacity of this conductor based upon the 90 degree C column because that is the ampacity of the conductor. I can protect, once I do that adjustment, say for example, excuse me, let's say for example, if I have a spreadsheet, which I've started, and I love this spreadsheet. I love this spreadsheet. Let's say if I had, let's start down here. Control C, Control V. Let's say I have 104 amps of continuous current. Why did I pick 104? Let's say 100 amps of continuous current. Well, no, let's leave it at 104. I don't like even numbers. Usually, whenever you do 100 amps, everything lines up evenly, and you go, well, that you didn't really teach me anything. So if I have 100 amps of continuous current, My conditions of use, my ambient is going to be 86 degrees. My number of race conductors in a raceway will say 2. We'll say it's a 3-phase. 3. My conditions of use tells me that the larger of the two is 130. So the conditions of use is 104 amps. That's my ampacity of the conductor. The 1.25 times 104 is 130. Now, if I throw this in a high ambient, somebody said I can have as high as 120 degrees Fahrenheit. Now, my ampacity of the conductor, which is based on conditions of use, is 126.83. And that's because I changed the ambient. I don't have the number of... so I can change this ambient. If I had 156, my multiplier goes down, which means now my ampacity, based upon the conditions of, not the ampacity of the conductor, what the required ampacity, not the ampacity of the conductor, the required ampacity needs to be 179. So if I do 120 degrees Fahrenheit, I need at least 126.83 amps of conductor for this application. But the larger of the two, which is your 210 and 215, tells me 130. So my minimum conductor size to meet 130 amps is a 2, a number 2. If I come over here and I select a number 2 copper, whoop, where's it at? Where's my conductor size? Here it is, right here. If I select a number 2, my 90 degree C column is 130, which equals the 130 here, which is greater than my conditions of use for my ampacity. The equipment, if I'm in a 75 degree C equipment on both ends, that tells me I can't exceed 115 amps for a number 2. If I land a number 2 in a piece of equipment that is 75 degrees C, and that's my weakest link, I can't exceed 115 amps through that termination. That has nothing to do with the ampacity of the conductor, but it is a limitation for the circuit. So what I'm going to focus on right now is the ampacity is 126. Why do I have 106? T44 times K44. Oh, that's what it is. The ampacity of this number 2 is 106.6 amps. That does not exceed the 126 that I need based upon the multiplying factors. So if I take this up to a larger conductor, if I put a 1 gauge in, now I have 118. If I take this up one more to a 1/0, now I've got 139 amps. That's not right. I'm going to put this back down to a 2. I was wrong. 106.6 is what I need based upon the conditions of use. 106.6, and I have what? 106.6, 104. That's not going to work because, yeah, it would work, because that's the ampacity of that conductor based upon the conditions of use. So I'm good to go. Because my 90 degree C column has to be greater than the 126.6. Not my overall ampacity has to be greater than the load, right? So I go to a number 2 based upon those conditions of use, and that gets me to 106.6 amps. If I didn't have the conditions of use, if my ambient was 86, now a number 2 can handle up to 130 amps. So if I'm based on 186, my minimum size for just the continuous load, I can make that a smaller conductor. But I'm going to leave it where it's at. I'm going to leave this at 120 degrees Fahrenheit. That tells me I need at least a number 2 to handle this circuit. And then I pick my overcurrent protective device, which, now, if my ampacity is 106.6 amps for a number 2, for a 2 gauge conductor, based upon those conditions of use, my ampacity is 106.6. 240.4b tells me I can go to the next higher overcurrent device on that circuit. So 240.4b would give me the permission to go to a 110 amp circuit breaker to protect this conductor at its ampacity. So over here, it says the next higher standard overcurrent device rating above the ampacity of conductors shall be permitted to be used, provided all of the conditions. Conductors being protected are not part of a branch circuit that supplies more than one receptacle. The ampacity of the conductor does not correspond with a standard ampere rating, which 106.6 does not. If it was 110, then I can't go to 125, the next higher standard. I'd have to stick with 110. This is greater than 100, less than 110. I can go to the 110 for the ampacity of the conductor. As long as I meet these three criteria, then the next higher standard rating does not exceed 800 amps. So that's the 800 amps or less. When I'm over an 800 amp, I cannot go to the next higher. It has to be equal to or greater than the rating of the overcurrent device. So I would have to go to the next lower. If this was 750 amps, I'd have to go to the lower value, not the next higher. Make sense? Beautiful. And that is B and C, and then D gets into small conductors. And what I like about small conductors, the small conductors portion of the code basically tell you what the overcurrent device is. They'll tell you if you have a 14 gauge copper clad aluminum, it's a 10 amp circuit. You have to have a 10 amp circuit breaker on it, and your continuous loads can't exceed 8 amps. If you have a 14 gauge, 15 amp breaker, period. 12 gauge copper, 20 amp breaker, period. Now you still have to adjust. If you're using a 14 or a 12 gauge copper, you have to adjust that for the conditions of use. You may have to go to a larger conductor because of the ambient temperatures. Be mindful of all of that whenever you're dealing with your proper overcurrent protected devices and selecting the right overcurrent device for the application. All right, copy link. Hopefully you got something out of this one today. We didn't get through all of 240.4, but we got through a heck of a lot. I've got to jump to another call. So again, thanks for tuning in. Thanks for joining in for this session around 240.4, talking about conductor protection and ampacity and all that jazz. Take care, stay safe, and we'll hopefully see you next week. All right, thanks Felix, thanks Steve, Dawn, everybody who participated and chatted in. Keep the chats going, comment on the videos. Love to hear your comments. Take care, stay safe, and maybe see you next week. Next week is Core Lane Committee meeting on Tuesday, so I might have to record the session. Thanks, Dawn. Thanks for what you do. Thanks for all of you guys, what you do for electrical safety and the industry. Take care, stay safe. See you next week.